Hello everyone and welcome to the CIE IGCSE 0606 additional mathematics course. In this video we will be covering the last chapter, which is chapter 14, calculus. So let's get started. Now I'll quickly introduce calculus as a topic. Um, okay, so calculus might seem a bit daunting and difficult at first based on what you've heard, but it's actually really simple once you get to understand it. So the first thing, I have an empty whiteboard here because it really doesn't make sense for me to, write it down. It's much simpler for me to explain it like this. But let's start with derivatives. So what a derivative is basically the gradient. Okay, it's the gradient of a function at a point. Okay, so obviously we have a line like this. Y is equal to some mx plus c, and we know that its gradient is m. So this is constant gradient throughout the line. So at all points on this line, the gradient is m. But if we had a curve, let's say y is equal to x squared, well, the gradient here is actually going to change with x, because to find the gradient of a curve, till now we've probably drawn tangents to the curve at that point and then measure the gradient of this tangent. And obviously the gradient of tangents to each point is going to be different. So a derivative allows us to algebraically find the gradient of a function at a point. So how do we find the derivative? Well, there are a couple of rules for that, but we'll get to those in just a second. First, I'll introduce some notation that I'll be using throughout this video. So let's say we're given some function f of x. So I'll write that f dash x. This is the derivative of f of x. It can also be represented as dy by dx. So what does this mean? Well, this says that we're taking the derivative of y with respect to x. So obviously x is the variable that we change to get a y value. Well, we're taking the derivative of that y value with respect to x. So you just don't need to understand what that means right now. Just understand simply that these two represent the same thing. Now there's another thing called the second derivative, which I'll explain to you later what it is, but this is the notation for it. So this is the second derivative of y with respect to x, and this is basically the derivative of the derivative. So what this means is we're just taking, this is the actual derivative function. So d by dx is what we said, the derivative of whatever is inside the brackets with respect to x. And so that multiplies out and we get this. Now, um, don't treat this like a fraction, even though it can be treated as a fraction. In some complex cases, this is actually a fraction. It's sort of paradoxical, where it's a function and a fraction at the same time, depending on the context. So just don't see that this d into dy gives us d squared y because of d into d, and then but dx into dx should give us d squared x squared. That's wrong completely. It's dx squared. Okay, don't get confused over there with that thing. Now we also have some limits. Essentially, you should know a general idea of what limit is. Basically, if you are given some x, and then x tends to some value n, and then you have f of x, well, you should also be able to find the limits of these functions, because that is what we use in derivatives, obviously. So this part is out of syllabus, but I'll explain it pretty quickly. But if we have a function y is equal to x squared, now this is called the method of first. These are the first principles. This is how we get the first rule in taking derivatives or doing the process of differentiation. I'll probably clarify that. Differentiation and derivative mean the same thing. Okay, differentiation and derivative mean the same thing. Differentiation is the name of the process. Derivative is what we get from the process. So if we're given a line y is equal to x squared, how do we find the gradient? Well, we can use the formula. If we're given some value x here, this will give us x squared. Then let's take some x plus delta x here. So this will be x plus delta x whole squared. Just assume that's delta x. So what will the gradient be? Well, by our definition, dy by dx, which is the gradient, be x plus delta x whole squared y2 minus y1 over x2 minus x1, right? But what is the derivative? It's the gradient at a point. We're taking the gradient across these 2 points. So what do? Well, we have to take the limit of this thing. So we take the limit of that whole thing as delta x tends to 0, because as delta x tends to 0, this point gets closer and closer to coming here, and eventually when it gets to 0, we're just at x. So we take the limit of this entire thing. I'll just expand it. So x squared plus 2x delta x plus delta x squared minus x squared over delta x. Right, the denominator is just delta x because x minus x is, well, 0. It cancels. So we have the limit of delta x tends to 0. So x squared minus x squared cancels again. So 2x delta x by x is 2x plus delta x. If you just simplify this fraction, and now we're saying that delta x tends to 0. So this just gives us 2x, because if delta x is 0, then we're just left with 2x. So what do we say? We say that f of x y is equal to f of x is equal to x squared. Well, then dy by dx is equal to f dash x, which is equal to 2x. And this leads us to the first rule, which is called the power rule. So the power rule states simply that if we have y is equal to x to the power n, then dy by dx will be n multiplied by x to the power n minus 1. And this is what you will be using most often for almost everything, really. Um, Now there's a few things that we'll get to before we go into more complicated forms. But if you have, let's say, the derivative of f of x, some function f of x, plus or minus g of x, well, we can just separate these out so that it becomes much simpler to compute the derivatives easily. Now this may seem counterintuitive. Why compute two derivatives instead of just being able to do one? Well, in some cases these functions may not be able to actually, if we were given, let's say, e to the power x plus sine x, how would these can't add, so how would you do this? Well, you'll obviously have to split them and find the derivatives for each separately, and I'll come to how to do that in just a second. Again, if we also have derivative of some function f of x multiplied by a scalar constant k, you can just take that outside and just take that and just take the derivative normally. So we find the derivative and just multiply it by the scalar. Yeah, that should be it for these rules. Okay, so I'll also come to this, but this is called the product rule now. And the product rule states that the derivative of two functions f of x multiplied by g of x. Now note, you can't actually separate this as d by dx of f of x multiplied by g of x. There's actually a bit more complicated one here. So this just becomes f of x times the derivative of g of x plus g of x times the derivative of f of x. Okay, so it's actually the first function times the derivative of the second function plus the second function times the derivative of the first function, and that is the product rule. We also have the quotient rule, which deals with fractions. So if we had f of x divided by g of x, something like this. Okay, so this will be let me just reconfirm this. This is, just ignore this. So okay, so this will be g of x multiplied by the derivative of f of x minus f of x multiplied by the derivative of g of x all over g of x whole squared. So you don't actually need to know these proofs, you just need to remember these formulas. These formulae will not be given to you. Just ignore what I did there to get the formula, but you will need to remember these formulae. So an easy way to do that is just remember denominator times the derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. Obviously it's quite long, but there's nothing that can be done about it. Okay, now moving on to, I suppose, well, I'll just do some basic derivatives here for some simpler functions. So we discussed x to the power n, but I'll just do that again. So the derivative of x to the power n is nx to the power n minus 1. Now, the derivative of a constant, let's say a, so a is any constant, is 0. Now, why is that? Well, if you were to look at the graph for some line y is equal to a, you can see that its gradient is actually 0, and that is what derivative is. So, the derivative of any constant is 0. Now, let's take the derivative of sine x. So, what will be the derivative of sine x? Well, it's cosine x. Similarly, the derivative of cosine x is sine x. Makes sense. That's actually wrong. It's negative sine x. Yeah, that's yeah, it's a bit of confusing part, That's why sine x gives cos x, but cos x gives negative sine x. But that's just how it is. The proof you don't need to know. Then we also have the last function tan x, which is secant squared x. Now you may be wondering what to do about, cosecant, secant, and cotangent. Well, those can just be represented as 1 by sine, 1 by cos, 1 by tan, and you can use the quotient rule. We also have the derivative of e to the power x. Now, this may seem a bit surprising, but the derivative of e to the power x is just e to the power x. And that's actually why e to the power x is used widely and is considered a special function. This property is the entire reason why we use the number e. Similarly, d by dx of ln x. Now this isn't ln x, it's actually 1 by x. So need to remember that one. That's actually pretty useful. Okay. Now I'll also introduce something called the chain rule. And the chain rule we use is when we have some y is equal to f of x to the power n. So chain rule actually applies quite simply. We take the n, so it's similar to the power rule, but it's a bit more complicated. So we take n times f of x to the power n minus 1, but then we have to multiply the entire thing with the derivative of f of x. So that gives us the derivative of f of x to the power n. Okay, so that's the chain rule. The chain rule is actually more like this. So if we're given some y is equal to f of x, right, and then we say um can actually use an example here from the syllabus copy, but you actually have, so yeah, okay, so if we're given y is equal to 3x squared plus 4 to the power 1 by 3. Okay, so we said this, we take u to be that inside part, f of x. Okay, and then what we do is we find du, we find the derivative of u with respect to x using the power rule, we get 6x, right? And then we represent y in terms of u, which is this. So we find dy by du, which again using the power rule will be 1 by 3u minus 2 by 3. Okay, 1 by 3 minus 1 is minus 2 by 3. But our goal is to find dy by dx. Now this is where a bit of the confusion comes in. But yeah, this is what the chain rule effectively is. This statement here, and obviously you'll assume that this is, well, this is acting like a fraction. Du cancels, you have dy by dx, and it technically is, but it can't always be used like that, when we learned about second derivative right here, is it? Um, it doesn't actually work out like that. So that'll be, if you compute this, what dy by du, 1 by 3 u to the power minus 2 by 3 to 1 by 6x, and then obviously you'll substitute this back in here and you'll simplify this and you'll get a value for dy by dx. So that's the chain rule. Now if we come to more applications of differentiation, so we did the algebra. Now what is differentiation used for? Well, we find the gradient, right? But what is the gradient of a curve? Well, it's also the gradient of a tangent. So assume this is a tangent, like this. Okay, it's this is a tangent, right? We're assuming this is a tangent of the curve. So we got the tangent of the curve. Well, what about the normal to the curve? Well, the normal is actually perpendicular to tangent. So if you remember this formula, the gradient of the normal, m normal into m tangent, is equal to -1, where m tangent is equal to the first derivative. And yeah, that's an application. Now the use of differentiation is to find stationary points. So what are stationary points? Well, stationary points are what we also call turning points. So for this graph of y is equal to x squared, the stationary point will be here. So as you can see here, this actually had a negative gradient overall, right? But then it became a positive gradient. Well, the point at which it occurred is called a stationary point, and at the stationary point, the derivative is 0. So we know from the first principles that the power rule, the derivative of x squared is 2x. So we say 2x is 0, and this obviously just gives us x is equal to 0, and we can obviously verify that graphically. So if you're given a function and you are told to find its stationary points, find dy by dx equated to 0 and find the value of x. If they ask for the value of y, substitute back into the original equation and find the value of y. Okay, now there's also something called dx by dt. Right, what this means is that we're measuring this is the derivative of x with respect to time. So t here represents time, and this is basically the rate of change of x. Right, so if you're given, let's say, the population of bacteria. Okay, so let's say we're given the population of bacteria is our x, and we're given some population, and then we're given, let's say, some time later the population is this, and they tell us this is some exponential curve. Well, what's the rate of the increase of population? Well, that's just dx by dt. So this is again based very much on the question, but in this types of question is where you'll apply chain rule the most. Okay, now let's talk about the second derivative. So well, if we look at these two curves here, we'll recognize this. Y is equal to x squared, y is equal to negative x squared. So they have the same stationary point of 0, 0, but there's a difference. See, this starts off with a negative and then goes to positive. This one starts as positive and then goes to negative. So how do we know which is which? Well, that is where we use the second derivative. So if we see here, the second derivative of x squared will be the derivative of 2x, which is just 2 by the power rule. X times 1 is 2, 1 minus 1 is 0, x to the power 0 is 1, so we're left with 2. Similarly here, it will be negative 2. Okay. Now, as you can see here, 2 means it's like this. So if d squared y by dx squared is greater than 0, our curve looks like this. What does that mean? Well, it has a minimum point. You can see here, this has a minima because there's no point lower than this. This is the lowest point. Similarly here, this is the opposite. If it is less than 0, well, that is a maxima. there is no point higher than that on the curve. And this is, greater gives minimum tends to be lower. It is opposite, but again, another thing to memorize. Okay. And obviously in most questions you'll need to actually state this. So this um, either of these will have to be stated in questions that involve maxima or minima. Now let's move on to integration. Okay, this is where the actual difficulty comes in, and loss of marks based on a very simple mistake of a constant. But what integration is it's just the reverse of differentiation. It is the reverse of differentiation. So what does that mean? Well, if I tell you that dy by dx is 2x, and we know that 2x is the derivative of x squared, you can say that y is equal to x squared. So differentiation is going this direction, integration is going this direction. It's the exact opposite, or it's the exact reverse. And similarly to differentiation, we have a couple of formulae. So start off with the simple one, x to the power n. And so this is the integral symbol. This is, and it's basically an s. And come back to, again, you don't need to know how integration is derived. We discussed first principles, but I want to get into this one. It's a bit more complex, but this is basically x to the power n plus 1 divided by n plus 1. So in differentiation we multiplied it by n and then subtracted. Well, first we're going to add and then we're going to divide. And now integration has a special thing where you have to add plus c, where c could be any number. Now why is that? Well, if I give you the curve x squared plus 3 and then I give you the curve x squared plus 9, what is the derivative of these curves? This is 2x, this is also 2x. So what does that mean? Well, when we're integrating it, it'll obviously give us x squared, but which is it? We have no idea. That is why we add a plus c. Now this c is unknown unless we are given some extra equation, such as this point lies on the line, or this line intersects the curve at this point, or something like that. And then we obviously have integral of f of x plus or minus gx d of x. Same thing, just split the integral and remember to add the dx. Same thing with the constant. Integral k f of x dx is equal to k multiplied by the integral of f of x dx. Okay, now we don't actually have product rule, quotient rule, what to do when they're divided or multiplied. That is currently beyond the scope of our syllabus. So I'll teach you quite simply what to do for the other conditions. Well, what's the integral of 1 by x? It's ln x plus c. The derivative of ln x is 1 by x, so its integral will be 1 by x. And so if you remember these formulae over here, okay, these ones, where is it? These ones. Then if you just say integral of cosine x is sine x, integral of sine x is actually going to be negative cosine x. Okay, I'll do this over here. Where is it? So the integral of sine x will be negative cosine x plus c, because negative sine x will give you positive cosine x. So we're just taking the negative outside, because negative 1 here and negative 1 inside mean the same thing. And then if we were doing negative 1 here, this would be positive. And if we were to not, then that would be negative. And the integral of cosine x would be sine x. And the same thing continues for all of these. Integral of ex, e to the power x is e to the power x plus c. Integral of secant square x will be tan x plus c. Okay, now what to do when you're given something that should be used the chain rule. Let's say integral of 1 over ax plus b dx. What to do now? Hmm? So, valid question. Well, um, what you're actually supposed to do here is, well, if we compare it, what is this most similar to? It is quite similar to 1 by x dx. So, there's actually a simple formula here. Well, the integral here is just going to be ln x plus b divided by a plus c. Okay, because if we actually say ln ax plus b and we differentiate this, this will actually give us a ln ax plus b. Then we multiply, and that is actually going to be so this multiply a here, we divide the a here, it'll cancel to give us the original function. And how do we get this? Well, you use chain rule. In integration, there is no chain rule, so we actually just have to remember the formula like this. Okay, similarly, if we have integral sine ax plus b dx, well, we integrate it, negative cosine ax plus b, normally divided by a at the plus c. So why we're dividing by a? Well, we're dividing by the derivative of the inside. Remember here how in the chain rule we multiplied by the derivative of the inside here. Well, in the integration we're going to divide by the derivative of the inside. So if this, let's say, x squared, well, then we would be dividing by 2x, and fortunately we don't actually have that in the syllabus, but that's also needed. We also have integral of ax plus b to the power of n dx. This is also worth remembering, I suppose, separately from the rest. So we have normal integral power rule, plus 1 divided by n plus 1 times a, again the derivative of the inside, and don't forget the plus c. You lose a mark, at least you lose 1 mark for forgetting the plus c, and that is the basic concept of differentiation. Now, how do we apply it? Well, similar to how derivative is used to find the gradient, we use integration to find the area under the curve. So if I was given this point 3 here, I can find this area using integration. So I would say that the area would be the integral of x squared dx from 3 to 0. So far we have done what is called indefinite integration. We are now going to definite integration, where we put these limits such as this. So let's integrate x squared. We use our power rule, x to the power 2 plus 1 3 divided by the same 3, and then we put square brackets here. Now in definite integration we can omit the plus c because it'll actually get cancelled. This is actually x to the power 3 by 3 plus c, um, again minus x to the power 3 by 3 plus c, but the value of x will be different because first thing we do is we substitute 3 into x. We got 3 cubed by 3 minus 0 cubed by 3, so this is going to be 9. Okay, and as you can see here, the plus c is gone because the plus c, if we take here and here, it will have the same value because it's the exact same curve, and it will get cancelled off. And then 27 by 3 is just 9. So the area under this curve from 0 to 3 is 9. Now obviously this is a very simple example. In the actual exam we will have something a bit more complicated. Say something like this. So if you're given some curve like this, let's say weird curve, and you were told to find this area, say this is 5 and this is 2, you cannot straight away just do integral 5 by 2 f of x dx, find this, done. No, this part is under the curve, so what you need to do is you need to, let's say if this was 3, so you need to integrate from 5 to 3. Now this will actually give you a negative value because it's under, so we take the modulus here and then we just simply add 3 to 2. Okay, and then that will be the the sum of these two will be the total area that is actually needed to be found. And then in some cases we'll also have, let's say, a curve and a line, and we need to find this area. Well, there's actually a rule for this also. So if, let's say, we have equations like this: y is equal to f of x and y is equal to g of x. Now these don't need to be curves shaped like this. They can be lines, curves, any shape of any form. But the general formula here, if the intersection point is A and B, then this is just the formula. If you're given two curves, then you have to find the area between them, because what we're doing here is finding this area all the way. Sorry, wait, one second, one second. Um, we have to find this area, right? That'll be, so that'll give, so if you were to integrate g, yeah, okay, my bad, it's actually going to be the opposite. It's a top curve minus the bottom curve. Yes, yes, yes. Okay, it's the top curve minus the bottom curve, because if you were to look at this, the area g of x, I'll highlight in red, includes all of this plus this extra area here, and let's just assume this intersects on the axis, so we have this extra area here, and that is actually the area under f of x. So we have to subtract that because it actually isn't what we're looking for. Now that is well, integration. Now let's move to kinematics. So kinematics is completely separate, but it uses the concepts we learned here. So kinematics deals with three things: S, which represents displacement. So this is displacement. V, which represents velocity, and A, which represents acceleration. So you might be familiar, if you've done physics, with these terms. So we say velocity is displacement by time, acceleration is velocity by time. So if you remember, we discussed here dx by dt and differentiation, right? Well, this is actually similar. So what is the value of velocity? Well, it's the derivative of displacement with respect to time, or the rate of change of displacement. Similarly, acceleration will be the rate of change of velocity, or the derivative of velocity with respect to time. And then we can also integrate. So S is the integral of v with respect to t, and v is the integral of a with respect to t. And then we also have a is d squared s by dt squared. That is also another thing that you should know. So uh, you'll probably be given one of these three and then expect to find either the other two or only one, substitute some t-value, get some answer or something like that. In some cases you might also be given graphs. So if you're given, let's say, displacement by time graph, let's say some curve or something, y is equal to f of x, f of t actually, for some displacement, well, if you take the gradient of this, that gives you the velocity, and the gradient of that, which is going to be a straight line, is the acceleration. And then obviously the area, if we go backwards, the area under the acceleration graph will give the velocity, area under the velocity graph will give us displacement. And that is all of the calculus you need to know for additional mathematics. Thank you for watching.